In this example, we'll verify Stokes' theorem on a surface whose boundary has multiple components. So we'll take our vector field to be a type of angular vector field, so 1 over x squared plus y squared negative yi plus xj. But then our surface will be the annulus, or ring, A, where 1 is less than equal x squared plus y squared less than equal to 4. So we've got an inner radius of 1 and an outer radius of 2. So as before, the first step is to calculate the curl of f. And f here is a plane vector field, so we really only need to calculate the k component. So this will be negative y over x squared plus y squared, x over x squared plus y squared, 0 I j k. So that'll be, so this will only have a k component. So this is k times now. Okay, so del by del x, using the quotient rule, this will be something over x squared plus y squared squared. So derivative at the top, this will give x squared plus y squared, and then minus 2x times x, so minus 2x squared. Then we take minus del by del y of del y, or y, negative y over x squared plus y squared. So that's going to behave the same. So this will give us plus another x squared plus y squared, now minus 2y squared. But now these all cancel out. So in fact, the curl of this vector field is 0. So we don't need to even parameterize this surface because the curl, the integral, so I called it A. So this tells us already that this is going to be 0. So to verify Stokes' theorem, we just need to verify that the integral on the boundary is also 0. So we'll parameterize the boundary. Actually, first let me make a comment. So if we orient the surface like this, so the annulus like this, with normal vector pointing up, then remember that the induced orientation on the boundary is going to be counterclockwise on the outer circle, but clockwise on the inner circle. So, right, boundary of A is C1 union C2. And we'll parameterize C1 by R1 of T is cos negative Ti plus sine negative Tj, because negative because we want to go counterclockwise, which is the same as cos Ti minus sine of Tj. And C2 will parameterize by R2 of T is 2 cos Ti plus 2 sine Tj. So now the integral over the boundary of A of f dot dr, this is integral C1 f dot dr plus integral C2 dr1 f dot dr2. So that is, let's see, I always never give myself enough room to write things. Okay, so integral 0 to 2 pi. On the first one, so 1 over x squared plus y squared is 1. So the f part will be sine of ti plus cos tj, and then dr1 will be negative sine ti minus cos tj. Then, okay, so that accounts for this term. Then this integral over c2. Now we need to divide by 1 over x squared plus y squared, so that'll be 1 over 4. Now negative, so now this will be negative 2 sine ti plus 2 cos tj, it's the f part, and then the dr2 is dot negative 2 sine ti plus, yeah, so sort of the same thing, plus cos tj, and then this dt. So what is this? Let's see what this gives us. So we'll have negative, here we'll have negative sine squared and negative cos squared. So this dot product will all give us negative 1. Here we'll have, so this will be 4 sine squared and, oh, sorry, this is supposed to go away. And 4 cos squared. So here we'll get 4 and then 1 over 4, so this is plus 1. So we have plus 1 here and 4 over 4, so plus 1 here. So again, the integral is 0. And so notice that if we had taken the clockwise orientation on, if we'd taken the counterclockwise orientation on C1, then we would have gotten a plus 1 here and a plus 1 here, and then the integral would not have been 0, so Stokes' theorem would not have worked out if we had taken the counterclockwise orientation on the inner circle.